So, good morning, everybody. Seminar, probability seminar, ABP for the moment. Just let me tell you that from next week, time will change in Europe and the United States, but the seminar will continue at 16 UTC. In Brazil will be 13, 13. Okay. So it is a pleasure to introduce today Luiz Renato Fontes, who will talk about random walks in birth and death environments. Renato, por favor.
Thank you, Pablo, and the organizers of the seminar for the kind invitation. Let me just start by saying that my computer is saying that my network is unstable, so hopefully it won't come down. But in any case, if it does, I'll try to make do with the cell connection. Okay, let's see. So this is a work more or less in progress. It's a joint work with Maicon, Pinheiro, and Pablo Gomes, which are respectively just finished PhD student in São Paulo, and Pablo Gomes is a postdoc here. And so this is concern random walks in random environments. So the dynamical random environment, which are so there's a history for this subject, which I'll probably be very sketchy about. I'm not sure I'm the right person to really give a complete account for this, but so the goal for this work is to understand and eventually for this talk derive a CLT for a particular kind of random walk in a dynamical random environment, which is in some sense non-compact. So this is perhaps what's sort of different from many works in the literature. So I'll just mention here the little that I know about this is in general. So there are many results which are quite general and robust for these kinds of random walks, and but generally many of them take place in compact environments. I mean, this is not maybe not necessarily because people wanted to start with that, but well, because perhaps naturally it's a sort of condition that come up. And so let me just give you some list of names, which are certainly by no means exhaustive. So we have, I just grouped, made two groups, two lists. So the second list here is concern sort of a more recent, perhaps, or perhaps closer to what I know about these kinds of processes. But these are the second list of people have been publishing results on these kinds of random walks in environments which are given by which are correlated and given by normally some sort of particle system like the contact process or the exclusion process and other kinds of correlated or non-correlated process. So the particular case we're going to consider here are non-correlated random environments. And the first sort of list of people have been working in this, I guess, previously for more time, I guess, perhaps. And there are many results. So, but in some sense, the environment tends to be compact, and that gives you a sort of control over the jumps of the process, right? So so this is going to be an issue for in our case, because yeah, we won't have a sort of uniform control over jumps, but so we will propose a stochastic domination to be able to derive results like the CLT. And so one example of a random walk in dynamical random environment, which has been more or less recently considered, was this work here by these two authors, Bandyopadhyay and Zaitouni in 2006, and they were considering random walks in independent environments, which turn out to be also known. I guess perhaps they could be compact, but they're general. So but there's a condition there which doesn't include the cases that we're going to talk about. I mean, for this work, there's a condition which requires so it's an ergodic environment. So it's the environment is given by Markov chains, which involve one for each site of the state space of the process of the random walk, and these so they're independent, these Markov processes, but I mean, so one condition there is that the transition mechanism is the transition probabilities have to be in some sense absolutely continuous with respect to the ergodic, to the equilibrium measure. So that restricts the thing somewhat. So let me describe our model. So the environment is given by birth and death processes. The random walk is going to evolve in ZD. And so for each site of ZD, we would put a birth and death processes on N. So it's the usual kind of birth and death process where the homogeneous birth and death process, which jumps one step to the right, so the probability P, and one step to the left, so probability Q, and except at the origin, but P. So we need. I mean, we'll consider at first, at least, the ergodic case where for which P is smaller than half. So, and the process is just a continuous time mean zero random walk. The embedded chain is the jump chain is just the simple symmetric, not necessarily symmetric, simple, and not necessarily simple. It's just ordinary random walk. Okay, and you may keep in mind the simple symmetric case, I guess. But yeah, so there are results which are either require that or require that it's not symmetric sometimes. But in any case, well, most results which are I guess written down in Maicon's. I mean, this is the object of Maicon's thesis, and I guess for all the results there, which I'm going to talk a bit about, they concern, I guess, at least the mean zero case. So at first we suppose that it's mean zero, and sometimes we'll have to say that it's it's symmetric. Okay, so this is the jump chain. So in order to complete the picture, we have to talk about the jump rates. So the jump at site x at time t. So it's an inhomogeneous space and time. I mean, we're talking about a single a jump at a single site. So it's given by a function of the environment. Okay, the jump rate is a function which is actually decreasing to zero as with the environment. So that so it gets slower and slower as it moves farther and farther in the environment. Okay, and so one motivation for this was to this came when I got a visit from Elena Gigina, who was interested in looking whether we could have in a dynamical situation like the environment like this, we could have a trapping as in the Bouchot trap model, where, for which the rates are fixed in time, and well, if they have heavy tails, then you get you get trapping, and so the question was whether in this case we could have that as well. So we started looking at the case where f is actually exponentially decreasing, and the reason for that was actually in Maicon thesis you will find this situation there, but things can be extended more or less in the same way. And but the reason to consider these exponentially decreasing rates is that I mean, if you look at the if you look at the expected waiting time with the equilibrium measure for each site. I mean, it doesn't depend on the site. I mean, depending on the value of A, this could be infinite. Okay, so this would be somehow a mechanism for trapping, but of course, when you think a bit about what's going on, I mean, since we have this ergodicity here, then you don't expect this to be an issue, because even though you could sometimes be very far from the origin, and then very slow to move the particle. I mean, the environment by itself somehow tends to get out of those slow configurations, and then you expect to not have trapping and actually have the CLT. Okay, even this with A here quite large. I mean, and with expected jump time infinity. Okay, so this is the model and more or less the motivation, and the reason that we take f decreasing is just to be able to implement the domination that I talked about before. I mean, so certainly we don't have a uniform bound on the jump rates, which is positive, right? I mean, it's in this situation the lower bound is absolute lower bound is zero. So and this is, of course, you can't sort of so this is not a viable lower bound, right? I mean, if you look at the random walk with zero jump rate, it doesn't move, right? So this is an issue. So here's the first result with those conditions. So if we start with the, oh, by the way, I mean, just feel free to interrupt at any moment. Okay, so here's the first result, which says that if we start with identically zero environment, so every birth and death process at each site is at position zero, at state zero. Then we find then we have a central limit theorem, which is which I mean xt has mean zero, right? So it's, you just look at just normalize it with the usual factor, and then it converges to a normal Gaussian distribution with non-trivial variance. Okay, and this for almost every environment, and this is I mean the main argument is for this case here when the environment is identically zero, but with other initial environments identical zero, and but with other, I mean this extends as I will explain by to other initial environments which are not too unbounded. I mean as soon as there are enough bounded distribution, we can extend this case to other initial environments. Okay, so okay, and there are other restrictions to, I mean, to extend the results to two dimensions. We actually then need the jumps to be symmetric, and for other dimensions we require bounded jumps. This is just because of tools that we use to argue these results. So, but I'll talk more about this later on. So let me give you an idea of the proof with the zero initial condition. So with zero initial condition, we can set up a subadditive argument for I mean it's enough that we look at the jump. I mean the main ingredient for the argument is getting a law of large numbers for the jump times of the random walk. Okay, so we look at the time of the nth jump, and then there's a law of large numbers for that. So this converges to a non-trivial constant gamma here, which is the same one that enters in the perhaps I forgot something. I mean, sorry. So here, I guess, I mean, this results probably for the simple symmetric keys, I guess, because otherwise there should be another constant here multiplying 1 over gamma. But yeah, okay. So I guess, I mean, either this is for the simple symmetric case, or you have to put a constant here, which is, I'm not sure. In any case, it's a sort of a simple thing, sort of obvious thing. Okay, so once you have the law of large numbers, then the result follows using the martingality of xt. Okay, so it's sort of a, you need some argument, but it's a sort of a standard. So we need to prove the convergence law of large numbers for the jump times, and this is it's for this that we need the to start with the zero initial condition, and then we set up a subadditive, actually a superadditive scheme here, which is, so if you look for the, so here I have to be a little careful, because I mean, the idea is quite obvious. I mean, it's quite immediate if you think about it, but then in order to implement it, have to be a little careful. But let me just give you the rough idea. You look at the time that the random walk takes to take n minus m jumps starting from 0. So you wait at time jm. So you wait for the process to for the walk to give m jumps, which it does requires time jm to give, and then you at that time you bring all the environment down to 0. Okay, and then
Luiz, você está sem som e você caiu.
Caiu a
okay,
tua
yes.
tela.
So can you hear me and see the?
Now
So where did I?
You are talking about just a minute ago. I don't think we lost much.
Oh, okay. So I guess perhaps I was talking about the
But you started again with 0 or 0. You said.
Yeah. Okay. So we are looking at the jump times of this random walk, and we want to derive a law of large numbers for that, and we will use the subadditive ergodic theorem for this, and then we need to get the to find the superadditive here, superadditivity here, and it comes from. I mean, this comes down from the monotonicity that we assumed for the function of the environment, which gives the jump rates, right? So this is so the way to do that is to just look at this array of jump times for which we after m times after m jumps, sorry, we bring all the environment down to 0 and start over, and then we get these LMNs, and this is a superadditive array, right? Because it's the 0. Remember that f is the function of so the rate, the jump rate is a function of the environment, right? And it's so it's decreasing, right? So if you are at 0, that's where it takes the fastest, right, to jump. So in the end, what you get is that this is superadditive. I mean, this of course is a sort of a vague argument. I mean, so you have to make a specific construction for, with the dynamical variables, and in order to, but this is some more or less well you can do it. So it's not very complicated. So it's so once you get that, noticing that L0n is Jn, then you get by applying this subadditive ergodic theorem, you get the convergence, right? But in order to do that, I mean, there are many things that you have to check. So let me not bother with let me go to perhaps the nicest thing that you sort of less bothersome aspect, which is to control the time between the time that the expected time between two jumps by the random walk. Okay, so so this is the so delta n here is the difference between the so it's the time the process takes to give the nth jump, right? And we want to control in order to apply the to get the result. I mean, to verify one of the conditions of the subadditive theorem, you have to have a control over this, and that is done as follows. You first observe that. You see, so I mean, if you I mean, the time to give the nth jump, which is this distribution of this time here, is this is so we're looking at a so we're fixing the time and the position of the random walk at time at the time of the jump n-1, and then so the next jump is going to just so this is a homogeneous jump chain. So it's just given by the time to give the nth jump as this distribution here, where it's an explanation of this integral here, right? Which is the integral of the jump of the jump rate, right? Okay. And if we look at the at S computed at delta n, this is the standard exponential, mean one exponential, independent of the environment. Okay, so this is two things. So let's look at what goes on with in order to control the delta n, the expected value. So we want to understand how the environment is distributed at time delta n here. Okay, so this is starting from I mean, let me go back here. Starting from this conditioning on this two, on the time and the position of in the previous jump. Okay, so the next jump is just then. So yeah, so there's this picture to perhaps help understand what's going on. So in this picture, I'm in this x-axis here, I'm displaying the successive jump times of the environment, which is the birth and death chain, right? So this size here are just IID. I mean, these inter jump times are just rate one independent exponential, right? So this is and the process is at these times they're performing. It's performing the P and Q jumps of the birth and death jump chain. Okay, so perhaps it started at site K. Okay, here so suppose that you are at the environment is at site K at this time, and then it's then it gives so after this time it jumps to K plus 1. Okay, so at this time here it jumps to K plus 1, and then perhaps here it goes to K plus 2, and then it's then it comes back here at K plus 1. So I'm not I'm not being specific about the positions of the environment, but you can see here in the y-axis that's I mean, if you project these jumps in the y-axis the way suggested here, you see that that in the y-axis you get a again a birth and death process, with except that now the rates, the jump rates are given by this. It's a inhomogeneous birth and death process with the same jump chains, but same jump chain, but it has this f of k. F here is the function that we of the environment we're considering. Okay. So I notice that I mean so we want to know what's the environment that delta n here looks like. Okay. So this corresponds to looking at the environment. So this is the environment of the, that's omega, right? Omega at delta n, and but this corresponds to this other process, which omega tilde at s of delta n. Okay. So again, this is the same picture. So so this is what I just explained to you, and so this is the upshot here, that the environment at the jump time is corresponds to the sort of y-axis environment at time s of delta n, and this time here is independent of this. Okay. This is just a mean one exponential. Okay, so in order to get a domination, it's enough to prove this lemma, which claims that the environment. So if we start with let mu here be the equilibrium distribution of the environment, right? So of the birth and death chain, which is just a geometric distribution, right? So if you start with this equilibrium distribution for this process here, for the omega process, then the omega tilde process is bounded by it at the distribution of the environment process is bounded by it for each time. Okay, so this is a stochastic domination for each fixed time, and we prove this lemma here, which is actually it's we can show that it's actually the distribution of omega tilde is decreasing in t. So it decreases from. I mean, it's easy to see that the limit distribution of the omega tilde is also a sort of I believe it's also geometric, and below this one, I'm not sure it's geometric. In any case, so is something which is sort of amusing is that not only you have domination, but there's a monotonicity of the distribution of these omega tilde, starting with I mean, if you start with mu, okay, and so this is something that this sort of monotonic convergence to equilibrium looks like something that could be in the literature, but I did not find any. I mean, if anyone knows anything about this, would be happy to learn. In any case, actually the proof that this is decreasing in distribution comes from the argument that is Maicon's thesis, which actually is done for the exponential function, but it all indicates that it works for general decreasing functions, and there's a separate argument there's an alternative argument for getting only forgetting this, perhaps not only this, but perhaps this as well, but which is more of a geometric nature, using reversibility of the birth and death process. Okay, so once you get this this domination here, I mean, it follows more or less directly that that you get this domination, that the expected jump time at time jn minus 1 is bounded by the expected jump time of the first jump, starting with equilibrium, which is finite. I mean, it's also, I mean, it's easy to, it's sort of simple to prove that it's finite. Okay, so you get this domination argument. And perhaps I'll talk about the extension to other. So this, of course, these other results here are depend on the starting with identically zero environment, and because of subadditivity, but superadditivity actually, and for these J's, and but in order to extend this to non-zero initial environments, we need to put some conditions, so some boundedness condition in its and product. Perhaps it's not so important, but yeah. But keep these conditions in mind. I mean, so there are two situations. There's the two cases for. So remember that the random walk means zero. And if we are below 2 dimensions, the following argument works. It's so you want to couple two versions of the process, one starting with identically zero environment and the other starting with the whatever initial environment you're looking at here, and then and so this red, this initial portion of this. So here we're trying to depict the trajectories of both processes. So one is so they start together. They start from the same point. So for a while they may evolve together, but then because they're seeing different environments, they may split, and they are independent when they are separated. So okay, so this is so they're going to separate, and then after a while, suppose you're looking at a big box of dimension m. So yeah, so this is one dimension, but it should work with 2 dimensions as well. So yes.
Uma pergunta.
Of course.
Mas o teu passeio aleatório ele é simétrico, não é?
At this point, I'm asking only mean zero, but yeah, but at a point I will have to act, for 2 dimensions I will have to impose symmetry, because otherwise.
Yeah, but it's homogeneous. The jumps are homogeneous, right?
Well, I mean, yeah, the jumps are homogeneous. Yes.
So the trajectories are the same, but with a change of time only.
Let's see.
You want to couple, I mean.
Yeah, perhaps that would be perhaps an argument. Yes, let's see. Yeah, that's perhaps one way to do it. Let's see. I guess we considered perhaps not for this issue particularly, but yeah.
No, because you shouldn't have the two different trajectories. Only a difference in the same trajectory, a difference in position in time.
In time, yes. Right. Yeah, that's true. So perhaps you then you would argue that that the time difference is
Yeah, exactly.
is bounded somehow. I mean, because they're going all to be separated at all times, right? But then they're not going to be far from each other somehow.
Yeah.
Yes. Yeah. Perhaps that would. I seem to remember that we used that for something, but not perhaps for this one. Yeah. For this one, we I mean, yeah. So this is. Well, I mean, the way that things are written is from this point on, you wait for them to meet again, and when they meet again, the environments are coupled, because the environments couple very quickly because of the ergodicity condition. So it's okay, but perhaps your suggestion would lead to a simpler thing.
No, my suggestion would work in any dimension.
Right.
The difference would be
yeah, that's right.
But it will take a lot of time also, because it's time with a infinite expectation for them to meet again.
Yeah, that's right, but that's not a problem because because they are going to meet again, right? I mean, one into dimensions. Yeah, that's right. So that's why we needed the symmetric jumps into dimensions, just because we wanted to make sure that they're going to meet again, and with probability 1. So no matter how long it takes, as soon as they meet, the environments are already coupled. Okay, because so it's So this is the argument for 1 and 2. And in more dimensions, we use. So perhaps your argument would also work. And but what we actually use is these cut times in 3 or more dimensions, because the process is transient, and then then it has cut times, right? Cut times are points where the future and past trajectories are disjoint. Okay, so for example, this point here is a cut time, but not this one. And but there are infinitely many such, and then you just wait for the. At each cut time, you look ahead and see whether you have 0. You have up to a point, of a large point, large space here over the trajectory. You look for the to see where it's all 0, and then this has a bounded away from 0 probability of happening at each time, and different times things are independent because of the assumptions, and so eventually this will happen. As soon as this will happen, as this happens, then you do a sort of a coupling of the environment argument again, and then it works like that. So this would be the argument for. But we need bounded jumps in order to be able to use results about cut times, which require this. I mean, requiring in the proofs, right? I'm not sure it's really needed, but that's how the argument works. And let's see so about the environment seen from the particle at jump times. Okay, so we want to understand what to see what we can say about the environment as seen from the particle. So here is the particle at time after. So we have to look at jump times. I mean, we want to look at jump times. Otherwise, I mean, we only have results for those times, I guess. So if we look at the particle, so this is the position of the particle right before the jump time. Okay, So x of jn minus. So it's about to give the jump and didn't give yet. So the thing is the way that the process is defined. I mean, it's constructed. I mean, the random walk is independent of the environment. Okay, and then you just if you just look at the so we want to look at the environment. Between so we sort of centralize the space of around this position x of jn minus the position of the particle right before the jump, and then you look around between a distance L, and so L is fixed. So this is a black trajectory, is a random walk, a backwards random walk. Okay, So let's look at the environment. So we're looking at the environment at the jump times, right? Only at the jump times, not in between these jumps. So this is going to be affected only by. So suppose you look at I don't know the site here, the origin, and then at the origin. So if you're looking at the origin, so you start. So suppose you start from. So let us start with the product distribution, product of the equilibrium of the environment, and then so this is going to be, so this is the equilibrium, right? So at all times it's continues to be equilibrium until it reaches it's perturbed by the visit of the particle, a random walk particle. So then it gets disturbed, right? But it may be disturbed many times, but that's what it is. So and if you go to an earlier time, which is not very far from this time L. So suppose that L here is large time, and L prime is also large, but not very far from L. Okay, so this is so again this is I mean they're going to be so since we're starting equilibrium, so starting L. The process at L prime equilibrium, at time L, it's again equilibrium. Okay, so the difference between these two distributions at time 0 is just non-existent, right? Existent. There's no difference. And but of course, if you I mean, if you take an L2 prime here, which is much smaller than L, then it's then of course you I mean, especially in the case where the random walk is, say, it's coming back here, so it's mean 0, so it's going to at a point it's going to come back to this region, and so there's going to be a perturbation if you start with a random walk here at L2 prime. It's not going to be at time L, it's not going to be the same, right? It's going to be perturbed by the fact that saw a particle here. But then of course, I mean, if these L's are large, then I mean, you can find a time here where there's no perturbation between L plus M and L, and L prime is going to so as soon as it gets to L plus M, it's going to be perturbed, right? But then there's plenty of time here for the perturbation to wash away, right? Because of the ergodicity. Okay, so with this kind of argument, we show that if we start the random walk here at time 0 with the product distribution, I mean, this thing converges at. I mean, you have an argument here for a Cauchy sequence, right? For the process indexed by the initial time, right? So this is I'm looking at the time here backwards, okay, and and so we get this convergence of the environment seen from the particle, and the reason why we the reason why we get this control here over these. So if you start here from L prime, when you get to L plus M, I mean, you need some control over the distribution here, right? But it's bounded, right? So the distribution at this time here, if we start from L2 prime, the distribution of the environment here is going to be bounded by the product distribution. So up to, perhaps I didn't say that before. So in order to get to L, you need, yeah, I mean, you have plenty of time to wash away the perturbation. Okay, so that gives you the yeah. So and then what you get is a perhaps. So what you get here is a distribution with a profile which should be bounded, right? I mean, it should be bounded up above by the. So let's say that this is this straight line here is the profile given by the product of equilibria of the environment. So the so the profile of the environment seen from the particle at jump time should be below it, right? And so this should be somehow the aspect of this profile. Okay, and so we should be able to say more. We should be able to say that this environment, limiting environment seen from the particle is not only below the product of the equilibrium of the environment, but it's absolutely continuous, right? Because I mean, when you get away from the origin here, you will the perturbation is going to be to have originated farther down, and then so it has time to wash away here. So this should be an. I mean, it's not actually written down, but I mean, it should give us an argument for this, and perhaps also we should also be able to say something about the decay of correlations of this measure here. I mean,
il tempo sta indo.
Oh, okay, yes. So I'm about to finish, I guess. Okay. So this is the result about the particle, and so that this is actually the environment seen from the particle, and that this is the last slide, and so questions which are only partial results. So the what about the when the environment is not ergodic? So it's so when P is larger than 1/2, so the birth and death process is actually transient. So it's if F is summable, then the process comes to a full stop. This is a sort of simple thing to show, and so otherwise we do get some partial results about the behavior of the jump time. So the process will jump infinitely often, but and we get some results of the order of magnitude of these jumps. And finally, the original motivation was to find some trapping, which we never did here because it's always central limit theorem behavior, and but there are some possible ways to get that with if you start with a homogeneous birth and death process, or perhaps other kinds of process like house of cards with heavy-tailed equilibrium distributions. Then I guess there's a mechanism for trapping. There's also there seems to be also a mechanism for trapping with instead of F decreasing, F increasing, and but in a no recurrent way for the environment. So of course there are other questions like correlated environments but I have nothing for those. So I guess I stop here. Thank you.
Thank you very much, Renato. Very interesting talk. So let's thanks, Luiz Renato, for that. Is there any question or comment?
So maybe I'll ask you, Luis, about these trap models. So do you have a guess for or something more to say about these? Do you really expect it to have these?
Yeah. So there's a very sort of very simple situation where it's obvious that that you have trapping where so consider a one-dimensional a fully totally asymmetric random walk, so it only jumps to the right, say, and the environment is starting in equilibrium, but the equilibrium has heavy tails, right? So this is actually the trap model, right? So it's so you get trapping there. So what we would like perhaps to do is to have that for less perhaps for transient say random walks in 3 dimensions of mean zero, but say I don't know, any 3-dimensional transient. So or perhaps with more dimensions, I don't know, but we do have some arguments for higher dimensions, transient situations where it actually can control things. So perhaps yeah, but yeah, it looks like it's going to be there. We don't know exactly what we can prove beyond this very simple case.
And you expect convergence to decay model as you have in the usual?
Well, it should be the let's see. Well, if yes, so the yes in the say mean zero situation, the symmetric, say in 3 dimensions, perhaps simple. Then it should be to this sort of, what's the name of this process? It's sort of time changed Brownian motion with it's just sort of the usual limit of the scaling limit of the Bouchot trap model in this situation here. So I'm talking about the process in the full space, right? So it's not the K process. I guess it would be this sort of, I forgot the name, but it's kinetically. No, I don't remember the name. There's a name for that.
Claudio?
No, thanks.
Okay. Renato, no, in ese caso que você, in this case you were talking about that you jump only to the right and you have the invariant measure that is a product of geometrics, right?
Right. I mean, the thing I just told Claudio. No, this would be, say, the let's see, it should be the this would be anything that has a invariant measure which is heavy-tailed. I'm changing the environment.
Okay.
So it could be it could be the birth and death process, but within homogeneous jumps, so that the invariant distribution is.
Yes, I understand.
It's heavy-tailed.
Okay, so then you have a phase transition there somehow in some moment. Because
that's right.
If you have a heavy tail, but the birth and death process are going very fast, in some sense you should eliminate the traps or not.
if you want to
you get
speed up
speed up. You send it the rate of the birth and death, you send to infinity, say. Then it's like changing the invariant measure at all times. So you will not get trapped in this case. And so I ask if you have an intermediate thing between scale 1 and scale infinity for the rates of the birth and death. Okay, well,
I'm not sure.
You don't need to answer.
Well, we have this result. I'm not sure if it's the same kind of thing. When the environment is no recurrence, you get this. You have to rescale time in order to see the jumps because it's taking longer and longer to jump at each jump. So it's not a trap. I mean, it's sort of a trapping, but it's everywhere because the environment is increasing everywhere. And so this other thing I was telling Claudio is the traps are sort of sparse, but in this other situation here, you would have traps at every point and every time, and there are situations where we, depending on the values of f, I guess, this function here, where we do get some control of the jump times, and so yeah, but these are all in progress now.
Okay.
I'm not sure, but perhaps this doesn't answer your question.
Okay. Thank you, Renato. Is there any other question? Okay, if not, let's thank Renato again.
Thank you.
Thank you, Renato. Very nice talk.
And just remind that next week, the seminar time will change in Europe. Okay, it will be 1 hour earlier.
Yes, it seems also in the US. But it will continue at 13 in Brazil and 16 UTC, right? Okay.
Okay, see you next week. Thanks, Luiz Renato.
Okay, thank you. Bye-bye.